Okay, cool. So we're doing derivatives. We're going to do a little quiz on derivatives at the end of class here, and it's going to be a basic quiz. I'm not going to get into the weeds on some of these more complicated ones, like the ones that we're in the middle of right here. I think I'll throw in a quiz maybe next week once we've had a little more time to digest. So the ones this week will be a little more tame than those. But we were on the middle of this page and we had these two left here. And so I was going to start with that, but I'll just remind you that I extended the homework for Wednesday. So the homework for Wednesday is now due tonight. And I'm just generally flexible about those homeworks. So one more questions before we get started? Anything you want to talk about before we just dive into these here notes? Okay, so the thing with the ones on this page are we're combining chain rule with other more complicated things, right? And so the one on this, the next one on the page here, we want to think about this as being, let me get my pen going. This is being what's inside the square root. And we always think about square roots as the 1/2 power, right? And we do it that way because we can do a power rule when we have it like that. And that's something that actually is going to be on the quiz today. So taking a square root and taking the derivative means a power rule, thinking about it in terms of a power, right? An exponential. And then we use the chain rule with the inside piece being the exponential times the polynomial. And I'm sorry, that was the inside piece. That's what I meant to say. That's going to be the g function. And the outside piece, like what is that inside? It's inside a square root. And so it'd be like square root of x, x to the 1/2. Let me see if I can I get this, put that hat there last time, and now I think I can't move it. There we go. And this one ends up being tricky because then we have to use a product rule on the g function. All right, so this one ends up being a product rule. And it'll have an exponential with a power, and so it's also going to have a chain rule inside of it. And so the inside piece ends up being the tricky part on this one. And so let's just do the derivative of the outside piece first, right? So the derivative of f prime. Again, this is the kind of thing I like putting on quizzes. Just like that. And we've seen that a couple times. Let me know if that makes sense or not, but you bring down the power, subtract 1 off the power, right? No big deal. And so remember, in doing that, we're ignoring what's on the inside. The inside piece, we're just totally ignoring. And then we go ahead and we put it back in. And so let's put it back in. Oops. So it's going to be the thing we just wrote down. All right, so I'm just rewriting the f function. But I've left a bunch of room in there because instead of having just x in there, we're going to put the entire g function in, right? So it'll be this, this 8, e to the 2x times 8x cubed, right? So that's the first component. That's sort of the tricky part of the chain rule, is usually thinking about the outside piece, right? We kind of ignore what's on the inside, take the derivative, and then put the inside back in. Is that okay? One of the tricky things on this one is then the g function usually isn't as bad as this one, but this one ends up being a product rule. And so we do have to think a little bit more carefully about g prime then. That's okay. So then g prime ends up being, oops, not f prime, g prime. How much detail do we want to do here? I will just erase this here. Yeah, I'll probably end up going down into that bottom one, and then we can just add another page. Excuse me. So let me just do the detail there. So g prime then is f prime g plus f g prime. And yes, I'm writing the details out, and my hope is that you're doing that too. So that when you look at it later, it makes sense. Even if it makes sense now, we want it to make sense when we're studying for the test. We want it to make sense when we're studying for the final. We want to have these notes. And so, and you know, this is important because if you don't write this down, you might miss this part, right? This ends up being a chain rule. And this one's just an easy power rule. Thank goodness for power rules and exponential rules, so we don't have to do too much, but sometimes we got to do some chain rules. Let's see here. If we want to see the details on that chain rule, might as well just write it down, right? So let's do the chain rule. This is a chain rule with the outside function being e and the inside function being 2x. Right, and so then we take the derivative of the outside function, and then we plug g in. That just stayed the same, really, right? And then we account for it with the g prime. And so we put both those things together for this derivative, right? So the derivative of e to the 2x, I'm sorry, I messed up the derivative of g. This should just be 2. It's just 2e to the 2x. All right, it's getting kind of weedy. It's getting like really, feel like we're getting the weeds here. It's getting real busy on this page. Let me just pause here, make sure everyone's gotten everything written down, and then we can kind of summarize it all. Should we write down the power rule real quick there too? So the power rule right here is just 24x squared, right? Okay. I think we have all the pieces. So we can put it together in a final answer here in just a second. Can I just pause and see if there are questions? Yeah. So notice how the question for those who are online, the question was in this chain rule part, why isn't it the other way around? Why isn't it f equals 2x and g equals e to the x? And we talked about, this is something that's come up a couple times now. Notice how e to the 2x is in the exponent, right? So you're taking the 2x and you're putting it up into the exponent of e. And so that's implying it's being plugged into something else, right? In other words, if you did it this way, if we did f of g in this case, it would be that. Do you see that? See how that's different than switching it around? So the fact that it's in the exponent is sort of what's telling us that the outside function is the e1. Yeah, that one's a little bit tricky because it's an exponent thing rather than, you know, if it's like sine inside of there's something inside of sine, like I feel like ones like this are pretty obvious, right? It's very clear what's on the outside, what's on the inside. Just, this has come up a bunch of times. So if you see an exponential one with something in the power, the exponential is on the outside. Okay. All right, let me get rid of some of that stuff. Okay, other thoughts before we put it all together? We've got all the pieces. All right, I've got the G prime, it's a product rule with a chain rule in there, but we have the pieces, and then the F prime of G is at the top there. So let's just go ahead and write down the final answer. So, and I'm just gonna move this one down to the next page, just so I can have room here. So you might need another page here. So the final answer that we have of M prime is going to be F prime of G of X. So that first thing we worked on up top there. And I should have just realized how big this is going to be. We're going to need lots of room on this one. I'm going to slide this one over. F prime of G of X times G prime, which is the product rule. So it's going to be 2e to the 2x times 8x cubed plus e to the 2x and 24x squared. That is a big, big problem. I wouldn't expect to, I'm not going to like hammer you on one of those on a test or something, but there are a couple in the homework that will challenge you a little bit. That might be. Let me just sort of try to figure out how this. So this piece here is the F prime of G of X and this piece here is the G prime. And this one was particularly nasty because the G prime was a product rule. All right. Thoughts about that one? Questions? Let me see if the chat's going. Nothing in the chat. Okay. That might be the worst one or the sort of the hardest one on this page, just kind of looking at all the different parts there. So, you know, I wouldn't feel bad if that doesn't make it's not crystal clear, but if there's something I can clarify, this is a good time to, like, I just feel like if you get this one, you're in really great shape. Love to get some people there who are kind of close, but maybe something's confusing. Just wait a second here. Anything? All right. I'm going to throw another page in here, and let's just do the last one a little bit quicker. The last one's not as bad, so I'm going to just rewrite this one down on the next page. And so hopefully you can recognize this again as a chain rule because something's being squared, and we'll have another product rule on the inside, but it won't be nearly as bad because it won't be a product rule of a chain rule, right? So just kind of, we can do this one a little quicker. So this is a chain rule with the outside function being x squared and the inside function being, I'm sorry, we have y's in here. I should have done y squared. Y squared and the outside function being, the inside function, excuse me, cosine times e. And so, yeah, we're going to need another product rule, but this is a kind of an easy product rule. And this is the kind of product rule that I start off with on quizzes today, for example, low level, simple kind of product rules that are just, do you understand the basic rules? So anyway, let's do the f function first. So the derivative, just 2y, no big deal. And then we stick the g function back in. So it's 2 times cosine y e to the y. I feel like that's initially this f part, this kind of thing is initially the thing that's confusing people. But I've been talking to people a lot, sort of in office hours and stuff, and I feel like people are starting to get that. Okay. Is that all right there? Okay, and so then we just do a product or product rule on this one. And I'm just going to write the answer. This is the kind of thing we eventually just want to be able to do is like, okay, I know the sort of general formula. If you don't remember it, it's this right here. Right? I have that committed to memory, and I know I've written all over this now, but I know what that is, and if you don't know what it is, it's out in front of you. I'm just going to do f prime g plus fg prime, right? So f prime, so cosine prime is minus sine. So that's f prime g plus f g prime, right? E just stays the same. So I just sort of did the product rule without the details. Hopefully that's okay. And then you just multiply those two things, right? You multiply the two things we just calculated, the f prime of d of x and the g prime. Just put them right together, and that's the answer. Right, so then p prime is those two things multiplied. And I'll just remind you, I'm not super picky about simplifying. You know, we'll worry about simplifying things in the next section when we actually want to start doing things with derivatives. Right now we're calculating derivatives. Next section we do things with derivatives. That's really when we want to be able to manipulate and simplify things. Right now, let's just focus on the rules. All right, anything about these rules? What do you think? I think, and because I think the next thing that we're going to look at is starting to use it, if I'm not mistaken. We talk about higher order derivatives real quick. That's right. And then we'll talk about how to use it. Yeah. As in, you're talking about this two right here? Okay, yeah, so the question was, when you go from here to here, it's a little bit confusing because we're doing the kind of pluggy thing, and that wasn't what I really meant to say. We're plugging things into each other, which is confusing, right? So let's look at that real quick. So if f of y is 2y, right? When we plug something into f, you just delete the y. So there I am deleting the y, but I'm going to just leave a space for it. And then when we plug something in, we just put it into that space, right? So if we plug in g, for example, it just goes into the space. And so you should think about there being a parenthesis there, basically, right? When you remove something, it like makes a parenthesis, because then if you stick something in that's really big, it needs to be inside that parenthesis. And so that's the way we kind of think of this. Okay, yeah, it's 2, and then there's a parenthesis. And what is g of y? Oh yeah, it's this nasty thing. But yeah, it should be, when you take out the variable, think about putting a parenthesis in. I've done that most times, right? And I'm really encouraging you to try that when you're doing these problems. Other thoughts about that at all? How are we doing here? Okay. Let me just erase this part. And let's just talk real quick about higher order derivatives. And I think we did most of this next page, but then we can also finish off with this one maybe. Yeah, that'll be a good place to stop. Trying to remember what's going to be in the homework next week. See, this page, using derivatives to find maxes and mins, that's where I'm talking about using it. And so it looks like, kind of thinking about this class, we'll probably get to that in the next period. Okay, let's talk real quick about higher order derivatives. So all that means is you can take more derivatives than just one. And maybe we haven't quite seen this yet, but all this really means is, so far, let me just go ahead and use the highlighter actually. Like it says in this paragraph right here, we're really just finding f prime so far, and I'm now seeing a typo. This should say f prime of x. Right, f with one apostrophe, and it means the first derivatives. And we've also written it like this, d over dx of f, right? And so it's just worth pointing out, especially because we're going to start talking about the second derivative test and what the second derivative means. Note that you can take more than one derivative. And so let's say we had some function with derivative f prime, like we've been doing this entire time. The second derivative, notice how there's two apostrophes, is just taking the derivative of the derivative. I hate saying that word so many times, derivative. But that's what it is, right? That's what this is saying. It's saying, hey, if we do d over dx of something that's already a derivative, it just becomes the second derivative. Right? Maybe it's worth writing it down in words. So f double prime, you find that by taking the derivative of f prime. Right, so the second derivative you find from taking the first one. How do you think you get the third derivative? You take the derivative of the second one, right? So that's what it says in the second thing. You can find the third derivative by taking another one. And you can just keep going on forever and ever and ever, right? You can just you could take d over dx of f to the third, and that would be f to the fourth. And once we start getting past 4, we usually write Roman numerals up there. But you could just keep doing that forever. We usually stop at the second derivative in terms of implications and interpretations. Excuse me. But in some contexts, higher order derivatives have meaning. Folks, mostly what I'm trying to get across here is the notation, right? When you have another apostrophe, it just means you're doing another derivative, and you can just keep doing it forever. that okay? Your thoughts about that? So let's talk about the meaning. Yeah, let's do that real quick, and maybe this will clarify some of those things. And if not, we can come back to it. So let's say we have a function, f of x, right? Think about it meaning something. Maybe it's a population over time. Maybe it's the amount of money in your bank account, something that you care about, right? Well, we know that the derivative, f prime, tells us how f is changing, right? So to Josh's question was, how do people use this in the real life? The derivative tells us how the function itself is changing. And so we've interpreted this a few times already. Let's think about it as a bank account, right? Everyone wants to have more money. If you have some function that tells you the amount of money in your bank account and the derivative is positive, you're making more money, right? Because that means it's increasing. If it's negative, something bad's happening and it's going down. And so maybe this is more an investment account or something like that, right? And so the first derivative tells you how the function is changing. That means the second derivative, which we obtained by differentiating the first derivative, right? So what I'm trying to say here is the relationship between the first and second derivative is the same as the first and the function, right? So what I'm writing right here, the second derivative tells us how the first derivative is changing.
But how would we be able to find how the first derivative is changing?
So we have a function, we differentiate that. So the question was, how do we figure out how the first derivative is changing? We have a function. If you take the derivative of that new derivative tells you how the function's changing. And what I'm saying is, if you take a second derivative, it tells you how the first derivative is changing. And if we take another one, it just always relates back to the one before it in the same kind of way. And so one really easy example of this, to Josh's point, is if f of x is the position function, so it tells you how far you are from something, or you're driving from here to Worcester or something, right? And you have some distance function. Then f prime, what does f prime tell us then? What's the rate of change of position? What's another way to say that? Yeah, so f prime tells us how position is changing, which is velocity. Right, so if f is position, f prime would be how fast you're going, your rate of change, right? F double prime, which again is the differentiation of the derivative, it tells us how velocity is changing. What's another word for how velocity is changing? Acceleration, right? So acceleration tells us how, whether you're going to be going faster or slower. No, not necessarily. It tells us whether your rate of change is increasing or decreasing, right? So if you're accelerating, that would mean your second derivative is positive, which would mean your velocity is going up. Now these contexts are just in terms of like position, but we have similar relationships with other things too. So if it was like a population, then f prime would tell us whether population is going up or down. And then the second derivative would tell us whether or not that's getting faster or slower, whether the rate of change is getting faster or slower, I should say. I think that's really we're going to do a couple sort of specific examples and think about what those mean, but does that answer your question a little bit, Josh, about how this gets used a little bit? And the fourth derivative, I actually meant to look this up, I forgot. I think it's called, there's a word for fourth derivative that sometimes gets used. I'm not going to try to make it up. Ariana? Yeah, so we can write that down too, yeah. So then f to the third derivative would be how acceleration is changing. And there's a word for that. I can't remember what it is off the top of my head. Does anyone know what that word is? Called people wanted to say torque, but it's not torque. All right, and then I'll just look up one more thing. If this does it, great. It's the jerk. That's right. It's not the torque. It's called the jerk. So it's a measurement of acceleration changing. You can imagine if you jerk something, it's sort of thinking about acceleration. I don't know. It's called the jerk. I'm not even going to write that down because I'm pretty sure that's true. But anyway, most of the time, for the most part, we stop it at a couple derivatives. But it depends on the context, I guess, is the thing to think about. It depends on what we're talking about. Okay, so let's just do a quick example. How much room do I want here? I was hoping to have a little more room than this, but I think this is okay. So I'm just going to put a little line down the middle of the page and just do a couple examples. The first thing I just want to point out is that if you have a polynomial, so let's say f is 4x cubed, you can keep taking derivatives, but eventually it'll be 0, right? Because the power rule is just going to eventually make the powers go down to 0. And so let's just do that real quick, right? So the first derivative would be 12x squared. The power got lower. The second derivative, 24x, right? The power got lower. Third derivative would be 24. Now we just have a constant. And so then the fourth derivative is just 0. And every other one is going to be 0 too. And so the idea that eventually polynomials become 0 is different than other functions, which sometimes get worse when you take derivatives. So in some sense, polynomials get better, quote unquote, or things get easier, or the function gets simpler at least, right? But there are situations where it just gets worse. So like, what about one like this, for example? Say we had just e to the x squared. Not even that bad of a function, right? Let's call that g. But if we do g prime, it's a chain rule. Okay, it's not horrible, right? But notice we won't do the details, but it ends up being this. Right, and so the power comes down and multiplies, the derivative of the power, excuse me. But then if we try to take another derivative, then it gets worse, because then it's a product rule and a chain rule. Right? And I'll just write that one down real quick. So f prime g plus fg prime, right? So f prime g plus f g prime. Let's make sure that looks okay. Yeah. And then if we did a third derivative, it'd be even worse, because then it'd be, you have two terms, it'd be a chain rule, a product rule, and inside that second product rule is a chain rule. So it's just gonna like snowball and keep getting bigger and bigger and bigger. So the difference between like a complicated function and a polynomial definitely manifests himself in the derivative. Right? And again, if you think about what the derivative means, it's the rate of change. Polynomials are kind of simple. Something that looks like e to the x squared is a much more complicated looking graph. And so there's more complex derivatives. Okay, and we end up using the second derivative a lot kind of moving forward. If you look down a couple pages, we've got something called the second derivative test, concavity, the second derivative test, all this kind of stuff. We're going to be taking higher order derivatives. So that's why we're kind of introducing it right before we do that. All right, I'm going to stop there. Can I clarify something about higher order derivatives or the work on there? Again, I didn't write the details on those chain rules or anything like that, but. Here? Everyone online doing all right?
Yep.
Okay. So the next page is something we had already touched on. We already sort of jumped ahead and looked at the equation of the tangent line. And it was following these 3 steps. And I realized that that's a confusing thing for a lot of people. It's pretty standard or common for that to be a little confusing, but at some point we gotta nail down these 3 steps right here, like it says, and be able to do that. And we skipped over this example because it was a little premature to do. And so it's actually part of the example I just did a second ago, right? 2x e to the x squared. That was this example right here. And I actually already did the derivative, right? And so I'm just going to sort of give people a minute to think about this because this is one of the things that's in lots of the homework, but it's one of the things that people are really struggling with. And I feel like at this point, having done some homework, having looked at some product rules and all this kind of stuff, we should feel okay about a problem like this. So anyway, give this one a try. Let's remind ourselves how to do it. We're going to find the equation of the tangent line. Let me erase this part. Go away. So you find the derivative. Again, I just did it a second ago. You plug in the point we care about. At this point, the point we care about is x equals 1, right? Because it's g of 1. And then you use the point 1. The point is going to be 1 comma g of 1 to write the equation of a line. And I would just use the easy version of that equation. I would just do the y minus y1 equals slope times x minus x1. Let's just spend a few minutes trying these 3 things. There are the 3 steps. See what you can do. I'll sort of just wait a minute and then slowly start writing the answer down. Again, I just did the derivative on the previous page, so hopefully you have that. Just gonna slowly write it down if you want to check your work, but you really should kind of have a decent idea how to do this by now. So you take the derivative, product rule, it's the thing we just did a second ago. So write that down. That's not right. Just plug that number in. And I did this before, and so I plugged it into a calculator and got approximately 10.87 if you'd rather work with a decimal. All right, so that's the slope. All you have left to do is figure out the y value you need to use, right, which is just doing this, plugging in 1 into g, and then just put all the stuff into the point slope version of the line. Not too bad. I'm just going to pause there and let you think about that, and hopefully that'll help with some of the homework that's left for this evening. I clarify anything before I sort of slowly start writing this down? So the formula of the line there says we need a slope and we need a point. We have the slope, 10.87. We have the x value of the point, which is 1. We just need to figure out the y value, right? And so that's where plugging in the point comes in. So we plug in 1 into the original function. So it becomes 2e to the 1, which I also did ahead of time. Let me see, remind myself what that is. So that's approximately 5.4. And so that's your y value. So the point you're going to use is going to be the x value we're given, and then that corresponding y value. All right, so we've got the slope, we've got the x and the y, we just plug it into that function, and that's the end of it. So then the slope of the line is y minus the y value equals slope times x minus the x value, where it's just 1. That's what's called, and this is, I don't know if you guys are familiar with this one. I am used to y equals mx plus b. I feel when I grew up, we hit y equals mx plus b hard. This is called point slope form. And it's one that doesn't get used as much as y equals mx plus b, but it's, in my opinion, a lot easier. You don't have to find the b. The other thing I'll point out is, because a lot of people seem to be struggling with finding the b. I've done a couple examples, a handful of examples of how to do that. I'll just point out, though, if you do the point slope form, you can just solve this equation for y, and that's another way to find y equals mx plus b form, right? So if you just take this and you just solve for y, just get y by itself, you could just translate this right into y equals mx plus b. Right? It'd be y equals 10.87x minus 10.87 plus 5.4. Right, just getting y by itself. And then that just looks like 10.87x. Let's see, I'm not going to do this math in my head, 5.47. So it's a nice, it's sort of a different way to get the b if you like thinking about it that way instead. Any sort of general questions? I feel like at this point, the homework that's due this evening should feel obtainable. Can I clarify anything from this section? All right. So let's see here. Doing well on time. I just want to introduce the next idea. I feel like if I just introduce this next concept, it'll make the next section go a little bit more smoothly. So I'm just going to probably run through this page. There's not really anything to write down here. We're going to add some notes to this picture. But you can see we're really moving into the good stuff here. We're starting to use derivatives, analyze functions. That's like one of the big parts of calculus. It's one of the reasons you're probably in this course just based on your own major, if your own major sort of sent you in here. So you can think about finding maxes and mins and what those implications are. So I'm going to summarize what it says in that paragraph here, but generally speaking, when we have a function, we're interested in knowing the interesting parts about it, right? Because of the function, again, think about some function you care about. It represents your bank account, the population of an animal that you like, the amount of disease that exists in society, right? Whatever it is, some function exists that describes that. We might want to know where's the biggest point, right? When is there the most number of sick people? When is the population going to be at the highest? Or the sort of the flip side of that is the low points. When's the population going to go down? When are we going to get rid of coronavirus, right? When is that low point going to happen? And so that involves finding max and mins. Now we call these max and mins. We don't just use the word max and mins. Let me go ahead and highlight a few of the words in here. We think about these in max and mins or discontinuities, right? So those are what I would consider the interesting locations on a function, because those are the places where important things are happening. Those are referred to as critical points. And so in the notes and homework, all kinds of things, it often says, find the critical points. And what I'm saying is the critical points are the interesting points, which are the maxes and the mins, and the places that you can't plug numbers in, the discontinuities. And so I've got just a hypothetical function drawn right here. And I just want to look at that picture and talk about what the critical points are. And then what we'll do next week, what we'll spend pretty much all of next week doing is thinking about how to find those points and classify them. So, okay, and again, think about your favorite function. I'm going to think about an animal population. So this is some animal population being graphed out. Maybe it's time on the x-axis, right? And the y-axis is like number of animals. Let's talk about maxes and mins. So there's this concept that I'm boxing in here of a global max and a min versus a local max and a min. So first of all, a max is a place that's on the top of one of those peaks, right? So let me draw a dot on the place where there's a max, right? Those two peaks, where I just put a red line, is a max. So I'm going to write the word max there. But let's classify them as being a specific type, right? So there's local versus global. Local means it's on the top of a peak. And so they're both local. Global means that one of them is the biggest, right? So think about the biggest on the globe compared to just the biggest around you, right? So this one on the left is the global max because it's the biggest one. It's the biggest peak, right? And the other one would be the local max. And so it's important to note that every max is a local max. And what I'm saying is there's only one global, okay? And the same thing applies with the mins, right? So let me just throw another color on there. The mins are just the same idea, just on the bottoms, right? So these are both mins, minimums. And then there's the concept of the biggest minimum, right? The smallest one, the one that's the farthest down, and then local mins. And so the one on the left is a local min, where the one on the right is a global min. Right, so again, the idea between which is the biggest one compared to just the top of a peak, and which is the smallest one compared to the smallest overall. We feel okay about the difference between kind of local and global max and mins?
Yes.
So what does this have to do with calculus? That's what it says in this next thing right here. This is kind of the important, not the important thing, but this thing right here is linking it to this material that we're learning. So in order for something to be a max, the graph is going up before that point and then is going down after that point, right? Like if we just zoom in on this piece right here, if I kind of highlight a few pieces, we're going up right here and down right here. And so on the first part of it, the derivative is positive. Kind of getting back to Josh's question, how do we use this? Well, if we're walking up towards a max, the derivative is positive. And if we're going down after a max, the derivative is negative. So what happened at the max then? It's zero because the tangent line flattens out. And so this is getting at the idea of the first derivative test. We find these extreme points by looking at the places where the max is zero. I mean, the derivative is zero, excuse me. And so I'm just showing you that in the picture, and that's what it says right here. Right? In order for a function to be at a max, we have to be increasing before it and decreasing after. So increasing before a means the derivative is positive. Decreasing after a means the derivative is negative. And the opposite is true for a min, right? Min means decreasing, flat, increasing. And so let's also make the note, at the max or min, kind of the big important thing here that we're really going to dig into next week, the derivative is zero. And so this is how we find those places. We take a derivative, we set it equal to zero, that's going to find our peaks. Thoughts about that? Seem okay? All right, so we've talked about max and mins. Let's look at discontinuities real quick. So that's the next point right here, discontinuity that I've highlighted in green right at the bottom. It says we have a discontinuity if the function or the derivative don't exist. And so it has to be one of those two things. So if we're looking for a discontinuity, we look at the function value or the derivative, and we look and see whether or not it exists. And we've looked at that previously, right? We looked at that in the continuity section. We started talking about discontinuities. And so on this picture, the discontinuity is where the dotted line is, right? This right here is the discontinuity. And so it's a critical point or an interesting part of the graph because it's a place where the graph doesn't apply, right? And so this is telling us something about a population or something. Wherever that point is doesn't make sense in this function. So it says something about function. It's function specific. Okay. What about this point? I actually meant to mention this before. This point right here. Is that a critical point? This one right here? It's not. A lot of people oftentimes think that this is a min, but notice how it does not satisfy the condition, this point right here, of a max or a min. Right? The function is increasing through that entire point. So this point, and I put that on there for a reason, because oftentimes I put graphs like this on tests, and I always trick someone into picking that point as being a min. So that point
because
right there.
Because it's not zero?
Yeah, so it's neither, exactly. So someone said because it's not zero. It's neither a max or a min because the derivative is always positive at that point. And we just said the derivative needs to be zero at one of those points. And so I just wanted to clarify that, try to get that out of the way in case there was a confusion there. Is it okay? Questions, John? There's one other thing on this page I just want to look at. It's the last point at the bottom here, which says sometimes we have a place where the derivative is zero, but it's not a max or a min. This is called points of inflection. See the graph above. And it says here, we'll define this later in 2 pages. We'll look at this a little more carefully. But let's just look at the picture again and think about where that happens. Right, so this point that I'm going to highlight on the right is what I'm talking about, right? So the derivative is zero there because it's like a flat point, or it's supposed to be a flat point. Maybe I didn't draw it so good, but it's supposed to be a flat point. But it's not a max or a min, right? It kind of like goes up, flattens out, but then keeps going up. And so this is what's called a point of inflection. And we'll look at this later in 2 pages. I'm not going to talk about it right now. But it's important you label that because when you go back and study this and you're preparing for a test, this is a nice picture to look at to kind of understand the differences. And in 2 pages, we'll learn about points of inflection. And so when you go back at this later, you'll be like, oh yeah, that's a point of inflection. Anyway, we're going to spend all week next week looking at finding these things, classifying them, using the derivatives. So it'll be a critical, it depends on the type of point of inflection. I don't want to get too much into it. This particular one on this page will be a critical point because the derivative will be zero there, but it's not a max or a min, is what I'm trying to say right now. And again, we'll dig into that a little bit more in a couple of pages. Yeah, I think I'm going to stop there for right now. And so we'll pick up on Monday talking about how to do that, right? The first thing we'll do is how do we actually do this stuff? We'll go through some examples. This is good stuff. Great. Okay. Can I clarify anything from this page? We're going to do our quiz in just a moment here. Open notes, of course, folks who are online, if you would turn your cameras on and start getting ready for that. And I'm just, again, can I answer any questions before we do that? I'm gonna start passing this thing out. Just make sure there's nothing in the chat. Good. I feel like if you've got your homework,